we're going to be going over homework problem 6. So we're also going to be generalizing it. So we'll start with problem 6 and see what we can generalize. So we had a set that was of size 8, and we had subsets of size 5, and we also had it so that no element could appear in the intersection of 4 of them, right? So what that also means is that an element can only appear max 3 times, because if it were in 4, the intersect those 4 would be looking for. So how do we do it? We took our 8 elements, we repeated them 3 times, and then we divided by the length of the subset. And then we ended up with 24 over 5, which is 4. And then from here, we had to show that there was some collection of 4 sets that made it work. So we're going to try 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. 3, 4, 5, 6, 7. And then 1, 2, 6, 7, 8. And then these are going to be our 4 sets, and they work. So that's how we approach problem 6, and now we can generalize it. So we're going to be generalizing this, and I'm going to leave that to Kevin to do that. We're recording.
All right, thanks, Ron. So what if instead of a set of 8 elements, we wanted some arbitrary number? And similarly for the other fields, we want instead of 5 being the size of the subsets, just any number k. And what if the max instead of 3 was such some number p, so that we have n, p, and k? Well, we can still find the total number of subsets that we can make. We just follow the same process using these arbitrary numbers. So we multiply 8 and 3 to create this total pool of elements that no matter how we slice out these subsets, no element will appear p plus 1 times, because there's only p of them that exist in the total pool in the first place. So to create our total pool, we'll do n times p. And since we're splitting it up into k-size subsets, we'll just divide the whole thing by k. And now, since we can't make a subset of size k with less than k elements, if this division is not perfect, if there is some kind of remainder, we'll just disregard those elements by taking a 4. Because you can't create a set of size k with less than k elements, which this remainder will definitely be less than k. Because if it was greater than or equal to, it'll just roll over and be, once again, be less than k by subtracting k. So by this formula, we have our t, which is the total number of, or the maximum number of subsets that you can make, which satisfies all of our conditions. And now let's try an example with a couple numbers. So let's say that n is now 5. Let's say p will be 3. Let's say k is 4. Well, now we can just plug it straight into our formula. To get our total pool, we do 5 times 3. And since we're splitting subsets of size 4, we take 5 over 4, and then take the 4. So 5 by 3 is 15, over 4 is about 3 point something, but we're taking the 4, so it gives us about 3, or exactly 3. So we see that by our calculation, the maximum number of subsets that we can make using these numbers is 3. But now we'll show you an algorithm that we came up with to find an example of such subsets that fulfill our conditions.
Okay, so we copy the elements of the set p times. For example, in the example Chen just demonstrated, we then take each successive group of k elements and make a subset out of each of them. Right? And as you can see, no element appears more than 3 times. The reason this works is because k is less than or equal to n. That means that n p over k is going to be greater than or equal to p. In the multi-set, we only have p copies of each element, so no element can appear more than p times in the at least p or more than p subsets that are generated.
So in this video, based on the process used to solve problem 6, we derived a formula for arbitrary n, p, and k, which gives you the maximum number of subsets you can create, such that no element will appear in the intersection of greater than p subsets. We also showed you an algorithm which will give you an example of such these subsets. Thank you.
Okay, so
What do you think? Was that too short?